The y-axis represents the potential energy content. The x-axis represents the progressions of the structural transformations of states through the transition state. You would notice two things. The energy level differs between S and P. If P is at lower level than S, the reaction is an exothermal reaction. One need not supply energy by heating in order to form the products. However, whether it is an exothermic or spontaneous reaction or an endothermic or energy requiring reaction, the S has to go through a much higher energy state or transition state. The difference in average energy content S from that of this reaction state is called activation energy. Enzymes eventually bring down this energy barrier, making the transitions of S to P more easily. Nature of enzyme action. Each enzyme E has a substrate S binding site is its molecule so that a highly reactive enzyme substrate complex ES is produced. This complex is short-lived and dissociates into its product, and the unchanged enzymes with an intermediate formations of the enzyme products complex EP. The formation of the ES complex is essential for catalyzation. E plus S, ES, EP, E plus P. The catalytic cycle of an enzyme actions can be described in the following steps. First, the substrate bind to the active site of the enzyme, fitting into the active site. The binding of the substrate induces the enzyme to alter its shape, fitting more tightly around the substrate. The active site of the enzyme, now in close proximity of the substrate, break the chemical bonds of the substrates and the new enzyme products complex is formed. The enzyme releases the products of the reaction and the free enzymes is ready to bind to the another molecule of the substrate and run through the catalytic cycle once again. Factors affecting enzyme activity. The activity of an enzyme can be affected by a change in the conditions which can alter the tertiary structures of the protein. These include temperature, pH, change in the substrate concentrations, or binding of specific chemicals that regulate its activity. Temperature and pH. Enzymes generally function in a narrow range of temperature and pH, figure 9.5. Each enzyme shows its highest activity at a particular temperature and pH called the optimum temperature and optimum pH. Activity decline both below and above the optimum value. Low temperature preserve the enzymes in the temporary inactive state, whereas high temperature destroy enzymes activity in because proteins are denatured by heat. Concentration of substrate. With the increase in substrate concentration, the velocity of the enzymatic reactions rise at first. The reaction ultimately reaches a maximum velocity Vmax, which is not exceeded by any further rise in concentration of the substrate. This is because the enzyme molecules are fewer than the substrate molecules, and after saturation of these molecules, there are no free enzyme molecules to bind with the additional substrate molecules, figure 9.5. The activity of an enzyme is also sensitive to the presence of specific chemicals that binds to the enzyme. When the binding of the chemical shuts off enzyme activity, the process is called inhibition and the chemical is called inhibitor. When the inhibitor closely resembles the substrate in its molecular structures and inhibit the activity of the enzyme, it is known as competition inhibitor. Due to its close structural similarity, when the substrate the inhibitor complete with the substrate for the substrate binding sites of the enzyme. Consequently, the substrate cannot bind, and as a result, the enzyme section decline. Example: inhibitions of succinyl dehydrogenase by malonate, which closely resemble the substrate succinate in structure. Such competitive inhibitors are often used in the control of bacterial pathogens. Classification and nomenclature of enzymes. Thousands of enzymes have been discovered, isolated, and studied. Most of these enzymes have been classified into different groups based on the types of reactions they catalyze. Enzymes are divided into 6 classes, each with 4 to 13 subclasses and named according by a 4-digit number. Oxidorductase dehydrogenase enzyme which catalyzes oxidorreduction between two substrates S and S. Example: S reduced, S oxidized, X oxidized, S reduced. Transferase enzymes catalyze a transfer of a group G other than hydrogen between a pair of substrate S and H dash. Example: S minus G plus G dash, S plus H dash minus G. Hydrolase enzymes catalyzing hydrolysis of ester, either peptide glycosidic C bond C, that is C halide, or PN bonds. Hydrolase lyase enzymes that catalyze removal of group from substrate by mechanisms other than hydrogenase, leaving double bond C C X Y X Y plus C double bond C. Isomerase, including all enzymes, catalyze interconvergence of optical, genetical, or positional isomerase. Ligase enzymes catalyzing the linkage together of two compounds. Example: enzymes which catalyze joining CO, CS, CN, PO, etc. bond. Ligase binding. Cofactors. Cofactors. Enzymes are composed of one or several polypeptide chains. However, there are a number of cases in which non-protein constituents called cofactors are bound to the enzymes to make the enzyme catalytically active. In this instance, the protein portions of the enzymes is called apoenzyme. Three kinds of cofactors may be identified: prostic groups, coenzymes, and metal ions. Prostic groups are organic compounds and are distinguished from other cofactors in that they are tightly bound to the apoenzyme. For example, in a peroxide and catalase, which catalyze the breakdown of hydrogen peroxides to water and oxygen. Heme is the prostate group and it is a part of the active sites of the enzyme. Coenzymes are also organic compounds, but they are associated with the apoenzymes in only transient, usually occurring during the course of catalysis. Furthermore, coenzymes serve as a cofactor in a number of different enzymes catalyzed reactions. The essential chemical compounds of many coenzymes are vitamins. Example: coenzymes nicotinamide, adenine dinucleotide, and NADP contain the vitamin niacin. A number of enzymes require metal ion for their activity, which form coordination bonds with side chains and at the active site, and at the same time form one or more coordinate bonds with the substrate. Example: zinc is a cofactor for the proteolytic enzymes carbopeptidase. Catalytic activity is lost when the cofactor is removed from the enzyme, which testified that they play a crucial role in the catalytic actions on the enzyme.